I'm Sheila Hollis, the Acting Executive Director of the United States Energy Association. I'm honored to be introducing the wonderful panel today, starting with Kristen Madler of USAID, a moment on what is USEA. USEA is a convening organization, nonpartisan and non-lobbying, and it works extremely closely with USAID, the State Department, and the Department of Energy in tandem to bring better living conditions, more safe, reliable, secure electricity throughout the world. And it's a pleasure to be here with you. And Kristen, I'm going to turn it right over to you now.
Thank you, Sheila.
Thank you.
Welcome, everyone. I'd like to thank you all for joining us here today. My name is Kristen Madler. I work in USAID's Global Energy and Infrastructure Office, and I manage our Energy Utility Partnership Program. And I would like to thank USDA for organizing this event and for their continued commitment and collaboration to USAID. USAID and USDA have been working together for more than 25 years to utilize U.S. public and private sector expertise as a critical resource to modernize sectors around the world. And we consistently hear from our partner utilities that this peer-to-peer engagement is highly valuable. Today's presentations build on a 15-part digitalization and cybersecurity webinar series with shared best practices on policy development, utility preparedness, and regulatory. And those are all available on USDA's website. And today's grid modernization session is the second one in our series. And grid modernization efforts really help to integrate all sources of electricity, energy storage, and distributed generation challenges, strengthen grid security, and provide a critical platform for innovation to deliver resilient, reliable, flexible, secure, sustainable, and affordable electricity. And utilities and energy companies have an unprecedented opportunity to invest in technology solutions that enhance the visibility and control that operators have across the electric system. And these technologies enable a range of new capabilities that can improve resiliency, reduce operational costs, and increase efficiency, and effectively enhancing the quality of electric. So today, our speakers will discuss an innovative project supported by USAID that enhance the security of the Republic of Georgia's transmission. Using a suite of smart technologies, the project greatly reduced the number, frequency, and duration of blackouts by responding rapidly to sudden and unexpected changes on the grid. And by doing so, it also increased the potential to integrate variable renewable energy on the Georgian network, work that USAID and USDA have pioneered in Georgia and other countries throughout the Europe and Eurasia region. So we think this project can be a model for many countries facing challenges similar to those faced by the Georgia State Electrosystem, the Republic of Georgia's transmission system operator. So in closing, I would like to thank today's electric power industry leaders for carving out your time to share your unique perspectives as panelists with us here today. We greatly appreciate your time and commitment. So thank you so much for joining us. And with that, I'll pass it over to Jake to introduce our esteemed panelists.
Perfect. Thank you, Kristen. Hello, everyone, and thank you for attending today's webinar. My name is Jake Swanson, and I'm a program coordinator at the U.S. Energy Association. I'm working on the Energy Utility Partnership Program that's based in Washington, D.C. Please note that this webinar is being recorded and that all participants are muted with their video turned off, but you're definitely welcome and encouraged to post questions or comments in the chat box or the Q&A box below. I'll be monitoring them and passing them on to our presenters as appropriate. You could find all of our Energy Utility Partnership Program webinars on our website at usca.org/EUPP/webinars. So today's webinar will cover the implementation and benefits of the Georgian State Electrosystem's, GSE's, emergency control system. And today we have the pleasure of having Eduardo Palma, who is the technical manager for the Latin America and Caribbean markets for Schweitzer Engineering Laboratories. And he serves international customers by sharing his expertise of power systems, wide and local area communications, automation, cybersecurity, and remedial action systems. We also have the pleasure of having two speakers from Georgia today. Alexander Didbaridze is the International Projects Technical Manager at GSE. And prior to his current role, he was the manager of the SCADA and Emergency Control System projects for GSE. And last but not least, we have Vladimir Kurinashvili, who is the head of system automation at GSE. And prior to his current role, he served as a relay protection and automation department engineer for GSE. And one thing that I will mention about GSE is that they were recently honored as our Volunteer Organization of the Year award at USDA's Public Policy Forum. So just like to congratulate them on that. And without further ado, I'll pass the floor over to Eduardo.
Thank you. Good morning. Can everyone hear me?
Yep.
Okay, perfect. Thank you. Okay. It's my pleasure to be accompanied by Alexander and Vladimir for this presentation. It will be a story that we want to tell to all of you about a successful project that has been a decade ago put in service. So there's a lot of history to this system. It is called an emergency control system, and there is another word for it, a remedial action scheme. It's a system that it's made for preventing blackouts. And it was installed in the Republic of Georgia as of 2011 in order to prevent countrywide blackouts, mainly on the transmission network. And the transmission network is owned by the Georgian State Electrosystem, 100% owned state company, which it's in the Europe region. My role here is to represent not only the solution, but everyone and of course, Vladimir and Alexander will be presenting as well. But let me start with the introduction. We will present to you a background of the system so you understand what were the challenges. And then knowing that experts such as Vladimir and Alexander were involved from the beginning, there were requirements for this ECS or emergency control system that were specifically tailored or custom to the solution that was requested. There's not a template in order to implement an emergency control system. It has to be tailored to the solution that to the application or to resolve an issue. We will see what contingencies were considered and how this system evolved. Evolved from distributed, which means that the control and decisions were being made by devices that were sparse or installed in different locations, geographical locations of the system. And then how it went to a centralized system that that was complementary or that was used as a way to modernize the system in order to expand to control more points, but did not replace the distributed system. How did we get to centralized? We'll talk about reliable communications or the core network that was implemented, network for transportation of very critical data that had to be received, processed, and then and then transmitted in order for decisions to be made quickly within 100 milliseconds. And what is the future of this system, this emergency control system that keeps evolving year after year? Starting with the background, we'll see here a geographical map of the Republic of Georgia, where to the north, we have the country of Russia. To the south, Turkey, Armenia, and Azerbaijan. Let me use my pointer. Turkey, Armenia, and Azerbaijan. And to the west, big hydroelectric plant called Nguri, that it's to the coast of the Black Sea. Since this hydroelectric plant is mostly most of the generation that it's produced in the country, and it has to be transported through about 500 miles long, 230 kilometers long lines in order for this power to get to the main load or the main consumers at the capital of Georgia, named Tbilisi. Then this 500 kV lines in blue color mean it is the lifeline of the transport of this energy. And backup, the 220 kV transmission lines also mean that there is a second path for the energy to be transported. There's about 8 substations counting transmission and distribution in the country of Georgia. 20 of them are just transmission substations. And Vladimir, if you would like to expand on my explanation. But I can continue. There is another thing very important to mention here, or to notice, that the country of Georgia is electrically connected to be a transport network between Russia, the north, and the countries on the south. So there are connections at 330 kV and 400 kV that do have contracts between countries. So it is very important for power to be reliable and for blackouts not to exist, not even brownouts. So as you see here, there's not only one way for the 500 kV lines to connect to the main capital, but there is a second path for 500 kV, making it a ring. A ring stabilizes the possibilities for this path not to be broken. But at the same time, we have to compensate the power that is generated with the loads that are consuming this power. So we'll go to the concept of power system stability that is very, very much related to resiliency. Yeah, as we see here, named by the IEEE Secret Task Force, stability or power system stability is the ability of an electric power system for a given initial operating condition to regain a state of operating equilibrium. When we think of equilibrium, we think things need to be stable. Voltage needs to be at a specific level, and frequency too. Two of the main values that are monitored at all times. And this to regain the equilibrium after being subjected to a physical disturbance with most system variables. So graphically, I show this this balance of two sides of the power system. Like in Georgia, geographically, you see the generation is far away from the loads or the demand, meaning the Nguri hydro plant, it's connected through a spring that it's the transmission network that at all times needs to be stable in order for the frequency and for loses balance. If balance is lost, then the whole system fails or falls down. When there's system faults through the transmission lines, this is causing that we need to compensate the system in order for the system to keep stable. But the compensation, specifically in power systems, needs to happen in milliseconds. Millisecond reaction times are a must, or they are required in system specifications when it comes to protecting a wide area network or a whole country. So in other terms, if we have the 500 kV line connected, but all of a sudden this 500 kV line loses connection, then we have to use an alternate path, which is the 220 kV transmission lines. So we call state 0 when everything is stable and everything is connected. But state 1, how do we manage for state 1 to maintain the equilibrium? Well, as we know, the power that is being transported needs to still get to the loads or to the capital. But the angle of the power system, the electrical degrees, it's going to change. So compensating means that we need to lessen the loads so that 200 kV network can transport energy to its destination. An emergency control system is a system that has been proven not only in the country of Georgia, but in many other countries. Specifically, the example here, it's measured by the numbers, but not only quantifiable by these numbers that tell you the story from 2014 up to 2021, how many total brownouts and blackouts have been present. As of April in 2021, our friends Alexander and Vladimir have quantified that this the benefits are that millions of dollars that were wasted when the country had blackouts or brownouts were 100% evaded, or they were they're not existent anymore, right? And this benefit is not only quantifiable in economic or in dollars, but socially too, because the Human Development Index, the HDI, for the country has increased at the same time. So with better power system stability, better economy and better social benefits to the country, to the citizens. Let's consider what were the contingencies. N-1 means that only one line or one connection between the generation and the loads could be disconnected. If there was a second fault or a second disconnection, then the system will fail. So what were the high probable contingencies? So what were the reasons why we have to protect and react in milliseconds? One of the examples is just the loss of the line, which does happen, and not only because of accidents, but because of weather. It is for GSE very important to be ready for the cold season, when the weather gets extreme cold and there's ice on the transmission lines, right? So power system studies were performed, and when you do perform them through experts, you arrive to lots of hypotheses that need to be validated. Most of the time they're validated with software that models a system, but the systems such as this emergency control system also do need validation through hardware in the loop testing, meaning that we inject these type of conditions that we consider the most important ones, and we verify the outcome in a loop back mode through feedback. And the feedback coming from measuring time of the control actions gives us 100% guarantee that when it happens on the real system, our models look exactly the same as what is going to happen in Georgia. So we do model these systems. We not only include power system studies. Angular instability and overloads happen, so they had to be compensated. There is a big concern or a big risk that neighboring countries would be affected, and there needs to be coordination between countries, between contracts that happen with the transmission lines between countries. So the emergency control actions basically are there to balance generation and load after these contingencies, the ones mentioned above. The validation through an accurate simulation model was a must. Not only a must because if you do not validate it before you install it, what you get is a system that once it is installed, does perform some actions, but they could be fine-tuned after the installation date. With a validation of the models before installation, at the moment of installation, on June of 2011, when it was installed, the system performed without any tuning to its specifications. So let's talk a little bit about distributed versus centralized. What does distributed mean? Well, it takes in consideration that there is going to be devices which are just special purpose microprocessor devices connected to currents and voltages, statuses hardwired to this box that have logic to understand thresholds. When a limit is surpassed, then they send via Ethernet communications an action to other devices that are connected to loads. So in order to compensate the balance between generation and load, you need to shed some loads or lessen the load of the generation system that cannot be transported through the normal 500 kV transmission line. When 220 kV is used, then shedding loads makes the balance that we need available in milliseconds. But installing devices that are distributed in a specific or very critical substations in order for them to work and send a signal to open the loads and for those loads not to be available was just the beginning, was in 2011. So would you like to comment on that, Alexander?
Well, shall we, excuse me. This is emergency control system, original emergency control system, which was developed in 2011, and we implemented ECS system initially for 2 lines. This was Imereti line and Kartli 2 line, as shown here, for 2 500 kV lines. So this was very small system, and as it was mentioned by you, the validation was not done prior to the implementation of the system because the ECS system itself was very small and was dedicated only to the very small part of the system. The actions, load shedding control actions also was very small, was touching very small part of the loads in the entire country. And saying briefly, this was a small system from the beginning, which when later was converted to the larger system with a central processor and central RAS system. So maybe this, maybe Vladimir wants to add something.
Okay. Do you hear me?
Yes, Vladimir.
Yes, Vladimir.
First of all, I want to thank you for invitation. It is a great honor for me to participate in this meeting. I want to add some words. During the high power flow in Georgian power system, the outage of 500 kV lines, especially Imereti, causes overloading of the 220 kV transfer network. That generally leads to blackout of the Georgian power grid. In order to avoid this fact, ECS sends signal to shed load and generation so that 220 kV networks will not be overloaded.
Thank you, Vladimir. One important thing that I wanted to mention and complement what your comments is that the original Ethernet network that was already installed or existing in order for these substations to be communicating to each other, or for the devices that are measuring the power system and then making logical decisions, was used and was implemented within 4 months. So it is very important to mention that if Ethernet or a fiber optic communication network is not existent, then it will be very tough to implement this type of messages that are Ethernet messages that are sent in milliseconds, so that a remedial action or an emergency control action is taking place. And another comment is protocols that are specifically used for transporting these critical messages to do such an action as to shed load are messages that have to get there within milliseconds. So not any protocol can be used. If I'm not mistaken, this implementation used the IEC 61850 Goose protocol in order to exchange values to shed loads. So it was used, we used a very interoperable protocol that is available worldwide.
Yes, correct.
Thank you very much. Now, let's look at the details on the distributed architecture. I want to make sure that that you guys understand that this distributed architecture was not taken away at all when the system evolved to centralized. I'm about to present the centralized system, but these number of lines and auto transformers, converters, and generators, they are all existing today as a system that is 100% available and complements the centralized system. So there is 8 100 kV lines, 5 500, 400, 330 kV interconnection lines that do the load shedding and generation shedding if exporting in the case of the interconnection lines. Also have HVDC control and have this connection to other interconnecting lines. This is very critical actions because they happen very fast. So they have to be able to use one of the most important and allies to an emergency control system, which is called dampening. Do you guys remember when I was talking about the balance that needs to be kept and there was a spring in between? Well, this spring will start to oscillate, but it will, if the system is strong enough and you shed loads to keep the balance fast enough in milliseconds, then there will be no oscillation because the dampening of the strength of these spring, which is the transmission system lines, will dampen the outcome. But if you let this oscillation or this unbalance to happen for a long period of time, if you don't catch it in milliseconds, then the spring will eventually start oscillating and will not be able to be controlled. So we have to control in milliseconds, and when we're controlling interconnections, there is more importance to it. You know. Well, it means the livelihood of other countries too. So there is one 220 kV line for load and generation shedding, as well as 2 auto transformers, 2 HDVC converters for load shedding if importing, generation shedding if importing, and 6 generators. Let's talk about centralized. Centralized means that there will be some logic on the devices that are hardwired to these currents and voltages and status of the power system that are remotely in the 500 kV substations, but they all report to one central controller. Central controller allows flexibility of adding more security and more lines of code in order to take in consideration more contingencies. Because in a central controller, we not only take in consideration the devices that are distributed in the power system, but we can complement this information with information from SCADA or from the information that the operators received. The central controller can make better decisions that allows for the system to be better, because it's not shedding an amount of load that is a little bit more than needed. It's precisely the total load that needs to be shed. So it's more selective. It's better that way. So the actions are put into a matrix in which the controller understands based on the power system conditions that are being reported very, very quickly in millisecond time into the controller, how to react. And the reaction will be sent via communications channels in order to shed loads and maintain this balance that we need. Both systems, the distributed and the central system, operate in GSE. This is complementary to what I've said before, and it's just a way of looking at the logic of how to do load shedding. Basically, there is a trip level or threshold of when we want to open the loads or disconnect the loads based on a pre-contingency power flow. And this goes into a logic gate, which is a comparison between if A is less or equal than B. A is different trip levels that are available to operators. It is very important to understand that a power system is constantly changing, and sometimes, not sometimes, most of the time, maintenance is being done. So if maintenance is being done and we have to tell the logic that operates in milliseconds, some of these original thresholds or levels have to be modified by an operator in order for them to be able to do maintenance on some lines and still compensate the, through other variables. The HMI that we're about to see is how an operator physically goes to a keyboard and mouse and types in the information that needs to be compared in order to open the loads or a feeder. Right here, I would like to open the mic for Vladimir or for Alexander to complement what I said, please.
Vladimir,
Okay, okay.
please go ahead.
There are settings of ECS. I would say, right. Okay, there are the settings of ECS at the picture on this right. Changes in setting of ECS are made from Georgian State Electrosystem National Dispatch Room, which is very convenient for dispatcher. If the mode in the power system is changed, he can make change in the setting of ECS in the shortest time. In this picture, we also see the state of 500 kV line on or off. On pink means it's on, and gray means it's off. Also, the messages are reflected in case of any violation in power system, which appears as a signal of the HMI of ECS.
Thank you very much. So there is situational awareness or a visualization that it's available in real time for the system to be reviewed. And at the same time, this type of software system allows in a centralized way to store information, historic information about the reports that happen and how they happen. Because we store reports of previous events, we can analyze them and compare these reports to how the system operates now in order to understand and quantify the benefits that were achieved in this system. It is important to show the system again as a geographic, in a geographic way, how the Black Sea is to the west and Tbilisi, the capital, is to the east, because we have not yet talked about the communication.
Eduardo, excuse me. Can I add a few words about the HMI
Sure,
system?
of course.
Thank you very much. The ECS HMI, this is the separate HMI system, which is not included into the SCADA or dispatcher's HMI system. This is very usual that some of customers prefer to have ECS HMI screens in the SCADA system, which is for dispatching only. The SCADA is for dispatching only. We decided to have separate HMI system providing data monitoring and control possibilities, and also, as Lado has mentioned, providing for the ECS operator possibility of changing of set points in case of changing of power flow in the system. So this is a full HMI with the full capabilities, such as we have in a SCADA system, for instance, but only designed for ECS purposes. So it is not connected to the SCADA HMI system. It is separate and standalone system. The operator in a GSC National Control Center, he monitors both systems at the same time, SCADA HMI and ECS HMI. This is what I wanted to say.
Thank you, Alexander. Excuse me, Jake, are there questions to be answered or should we wait till the end?
Yeah, go ahead. We have a question from the audience on why you would have separate HMI for the dispatchers.
We decided not to overload SCADA system because dispatcher, during dispatching, he of course does not deal really with the ECS HMI. The ECS system is a very fast system, operates automatically. Only the case when dispatchers involvement, interference is necessary for the ECS system. This is only the case when we have a change in the system of the power flow. Therefore, we decided that there is no really need for ECS signals to appear on a SCADA dispatcher's HMI screen.
Thank you for the question. I'll continue.
Yes, please.
The generation shedding logic, it's a logic that was installed based on megawatts or a measurement of power that we have in the power system that it's combining or combining the measured megawatts on the HVDC to the measured megawatts to shed based on the power system state of power system and contingency. At the same time, when an ECS contingency is detected, then the controller tells the system to combine this information in order to select a combination of the generators to trip. So it's not only load shedding. Sometimes you must include generation shedding. This is one of my favorite parts of the story, and it is a very important part because, as I said before, in the beginning in 2011, they were using Ethernet switches to deliver goose messages to trip. But what happened when we went to centralized? We had to upgrade the Ethernet network. This Ethernet network, has settings in each one of the devices that need a lot of coordination. And Ethernet, fundamentally, it's not a network that always has the same deterministic behavior on packet delivery. So since the OPGW, or the optical ground wire, meaning the fiber optic network, was already installed, we together with GSE decided to upgrade the communication transport network to the most reliable solution out there in the market, which is a multiplexer. The multiplexer that you see on the right not only offers by settings a way to allow bandwidth to be isolated for specific protocols that are being transported, so the availability of the communications on the transport of these messages are always guaranteed, because that bandwidth is only selected for critical transport of messages. But the Ethernet, this network also includes cybersecurity features, such as the use of firewalls, secure login, and secure and complex passwords. The engineering of the traffic was set through these multiplexers in order to create traffic segregation, and something that was very important also, time distribution. So it is a synchronous network. The synchronous multiplexers had a bandwidth, like I said before, to route critical goose messages, and a second network bandwidth through the same fiber optic cables to route TCP/IP traffic, the traffic that just that it's updated not in milliseconds, but in half a second or a second. Notice that on the physical network, or how these multiplexer boxes are connected one to each other, there is one per substation, and they match the name of the 500 kV substations, and some are in 220 kV as well. But since the best type of redundancy comes when you connect the multiplexers in a ring topology, meaning in a that they're closed loop. There is a primary. There's two paths or redundant paths in order for this information to get to its destination. So it raises or increases the availability time as well.
Eduardo,
What?
excuse me, may I say a
Yes,
few
please.
words, just a few words about the ECS Communication Network, which is based on SEL icon multiplexers.
Yes.
This communication network in GSE used for the protection grade systems. SCADA system has other multiplexer network, SDH multiplexer network. This is one more reason why we decided not to combine SCADA HMI with the ECS HMI. Since we are keeping these two systems separate and we have separate communication networks for them, we decide. So our intent was to keep these two systems as much as possible separate. No, since we have our communication network for ECS and for other protection degree systems, this was one more additional reason not to combine it with SCADA system. Therefore, we have separate communication, and we have separate HMI for SCADA and for ECS systems.
Thank you very much. These devices are manufactured to be installed in substations. They don't have fans and they don't have parts that could create heat, like with friction. So it is a specialized device in order to transport this information and have availability as a priority. And the device is called an SEL icon. Not only has it connected the country of the Republic of Georgia, but countries such as all 6 countries in Central America, Panama, all the way up to Guatemala, and other places of the world. So it's a proven solution. That's my point. Going now to what is the future of the ECS system, or the emergency control system. Well, as Alexander has just explained, they wanted to keep it separate, but there was some information from SCADA, existing SCADA,
Yes,
that is being shared into the controller in order for the controller to take action. The plan in the future is to disconnect the SCADA and have the central controller hardwire to those measurements that are coming from the loads. Would you like to add a couple of comments?
Yes.
Okay,
May I say?
Vladimir, go ahead. Yes.
Yes, as for today, centralized ECS depends on the SCADA system. There are cases when the SCADA system is lost. It means that the central ECS is out of service or out of action. That is why we want to make ECS completely independent. So in this future, we are going to replace measurements which are coming from SCADA to ECS. We need to install independent device. After that, we will disconnect SCADA from ECS and add new measurement for ECS to make the ECS system completely independent.
Yeah, as Vladimir said, we are keeping one connection to SCADA system today, 104 by IEC 104. This is connection for the slow information, actually we call it. Slow information about the loads for load calculation for load shedding. But how the practice shows that when SCADA system fails or SCADA servers are failing, we have a problem in a central ECS system. The calculations are not conducted in a central ECS system, and our ECS system automatically switches over to distributed system. This is one more reason why the protection degree systems and informational degree systems such as SCADA, in our understanding, to be separated.
Very good. Thank you. You have the mic open to talk about the synchrophaser metering system and wide area monitoring, how synchrophasers are an upgrade plan for you.
Yeah. Okay. I would like to tell briefly the story of previous days in order to understand how these two systems were connected. Today, our synchrophaser metering system and emergency control system are combined into one system. So the point is that we started ECS project about 10 years ago, and we based it on the SEL relays, as you know. We are not using in a Georgian ECS system synchrophaser measurements. However, the synchrophaser measurements, as you know, were provided by SEL relays used for the ECS purposes as an addition capability. So this capability we had been not using for the ECS purposes, as I said. But approximately about 4 years ago, we had a need for a wide area monitoring system, which GSE intended to use to study the behavior of generators and to study of disturbances in a 500 kV network. We have started the project of installation of PMUs, phaser measuring units, in order to have implemented wide area monitoring system. And here we found out that we can use ECS relays since they are providing synchrophaser measurements. So the half of the task was already fulfilled, because in half of the substations and outstations in the power plants where we have ECS relays and IEDs installed, we also automatically have possibility of acquisition of synchrophaser measurements. Later, during the project negotiations, we decided to use SEL PMUs for the purpose of synchrophaser measurements. So ultimately, we got the situation when the synchrophaser system is providing synchrophaser measurements and ECS relays are also providing synchrophaser measurements. So these tasks are provided by two systems, ECS and synchrophasers. And what is more, in the substations and power plants where we have only PMUs installed currently, in these substations, the PMUs we could use also for the ECS purposes in future. If we have in the future, we decided to put ECS system in these substations where we have only synchrophaser PMUs, we can use the synchrophaser PMUs also for the ECS purposes. So this is a kind of integration of two systems. Parts of synchrophaser systems can be used as an ECS relays, and on the other hand, ECS relays are capable to provide synchrophaser measurement. Therefore, it was natural for us to decide to integrate these two systems into one system, let's say. Thank you.
Thank you very much, Alexander. Well, not to make this presentation too long, I think we're at the end of the time allowed. And I just wanted to say a couple of words about synchrophasers. Synchrophasers have been in many countries a solution that allows an operator to be curious about things that they haven't seen before on their own power system, meaning that with regular SCADA information, you get magnitudes, you get values that are just magnitudes. But when you include synchrophasers, I'm sorry, when you look at a screen side by side and parallel with SCADA and synchrophasers, you'll notice that with synchrophasers, you have magnitudes, but at the same time, you have angles. And power system angles allows us engineers that know our own power system to detect things way faster than a change of magnitude. So if a line is disconnected, then the angle, the electrical angle is going to change. If there is oscillations, then electrical angles are going to change. And this information is also updated and time aligned, which is a lot, very useful, like Alexander said, on adding values in real time that are time aligned to get real resultants that do not have error because they have been added with a timestamp alignment to know that the resultant of adding values is true at the time stamp when they were added or multiplied or divided. So it is a very good upgrade, or something that it's useful from the beginning, but now they're taking a lot of advantage of. At the end, there is a web link for you guys to read more about it. We have a website that has the whole story. And another cool part about the story is that the gentlemen in this presentation are very very keen on testing their own system, because they did a live test of their own 500 kV line in order to 100% verify that it worked. And you can read more about it on that web link. I appreciate everybody's time. Thank you very much.
Thank you, Eduardo. We do have a couple questions from the audience. I see Alexander just answered one of them. I'll start at the bottom. For ordinary, oh, Alexander's typing that one out too. Okay. Are SDN or types of zero trust systems, are they used for cybersecurity?
In the Republic of Georgia, SDN has not been implemented, but the Ethernet switches that Schweitzer Engineering Labs or SEL provides for SDN are for only OT or operational technology, or for substation use. So that technology, thank you for the question and to bring up the subject, do provide cybersecurity by whitelisting only the traffic that it's allowed, and not allowing the first step of a cyber attack, which is reconnaissance. When you try to reconnaissance or see what windows and doors are open of your network in order to understand the network and try to find vulnerabilities, well, with SDN, we stop the reconnaissance at the door. We don't allow it. And that is one of the features of cybersecurity. I could go on, and SDN is one of my favorite subjects too.
Great. Thank you for that. And I had a question that might be helpful for our audience. What would kind of be the first step if a country wanted to implement an ECS? Is it power system modeling? Where would countries need to start?
Well, one of the most important parts is getting together with the system experts to understand their concerns. But if Ethernet or fiber optic or communications network does not exist from the beginning, then the investment sometimes it must go in order to create it, so that wide area communications transport those signals that need to be received and retransmitted in milliseconds. So that is part of the question, part of the answer, but a very important part.
Great. Vladimir, Alexander, any comment on that question? No, I guess not. Okay.
Yeah, I guess no, yeah, I have no.
Okay.
I have another question.
Yeah, we got one final question, and then I'll wrap it up. How can an ECS improve the capacity to integrate variable renewable energy?
Thank you. Great question. I appreciate it because I did not explain how good it is to have hydropower, meaning that you have inertia, and you can use inertia to your benefit in order for your power system to have a window that is longer than 2 or 3 milliseconds, or very short millisecond window in order to react. When those milliseconds start to shrink, then we're in trouble because we have to compensate some other ways. And what happens when you physically connect to in a distributed way throughout your country the distributed energy resources that might be inverter based, or the solar plants, the wind plants? They have an inverter, and inverter change DC to AC in a step change, meaning that it's very extremely fast. So the changes that happen to this balance that we're trying to keep are so they're going to be less controllable. And also the short circuit studies are going to be different when those intermittent generation stations are not available because there's no sun or there is no wind. So when they're not available, not because of a fault, just because of the weather, then we also have to compensate and do a lot of coordination. And this takes engineering, which we're good at, so we can take care of that.
Great, thank you, Eduardo. We've got one last question. Can you talk about the comparisons between local or inter-area oscillation compared to load and generation equilibrium?
Okay. When we have oscillations, is because we have interconnected countries. And these oscillations can come from many, they don't have to be local to your own country. They could be happening in another country that it's interconnected to another country that is interconnected to your country. So how do we make sure we catch them? Well, there is a technology that is the best technology to implement when you want to see and actually measure into a report that you can then analyze post-mortem, post the event. This technology is called synchrophasers. We mentioned it. With synchrophasers, what you receive is information from from a distributed network of PMUs or phaser measurement units that allow you to understand if there is what is the dampening in a positive value or a negative value of your power system when things happen, like, for example, disconnecting a transmission line, or for a generation plant to come onto the system. So when you talk about the difference between oscillations that are in two categories, benign and malignant, and those malignants are the ones that we want to take care of quickly. and the balance that you have to keep. They're interconnected. They are all part of the contingencies that we have to think of and categorize on priorities on a plan. And now that, for example, in the Republic of Georgia, they will be using more and more synchrophaser information, they will be able to see those electrical signatures that are basically a way to understand how oscillations come from Russia in the north, if they happen, or the countries that are in the south. And it is my personal experience that some countries like in Guatemala, that they have implemented oscillation detection and oscillation detection with control, that they know when things happen down in other countries of Central America and in the north in Mexico too. So it is not hard. We can do it.
In Georgia, we have, as I mentioned already, wide area monitoring system, which is detecting the oscillations in our power system. So which will be converted later to wide area control system, as Eduardo has mentioned.
Great. Thank you both for that. And then one final question. I know I've said that a couple of times already. But how long is load shedding in general, and is there any backup to be connected to the system?
Sorry, how long?
How long is your window for load shedding? I mentioned 100 milliseconds, but could you talk about how long you guys usually take?
60 milliseconds. 60 milliseconds from detection of the contingency to the control actions issued by the end device, ECS end device, let's say. It takes about 60 milliseconds.
Okay.
60.
Got it.
Very fast.
Yes. And everything is based on goose messaging. We do not use IEEE C37.94, which is preferable for other vendors. We would like to welcome everybody in Georgia and see how this system has been operating for many years, based on goose messaging. Yeah.
Great. Yeah, maybe we'll take a trip there after travel restrictions get lifted because of COVID. But but thank you all so much for presenting today. I think it was very helpful, and we covered a lot of the technical aspects, and I think in general, some of the recurring themes were definitely resiliency, and it was definitely a cost effective program to reduce the number of blackouts and brownouts, and there's a ton of other side benefits, but I will be posting the webinar recording and the presentation to the website, and I will email it all to the attendees. So thank you all so much for joining us, and hope to see you again next time.